Have you ever stood in front of a towering skyscraper or, even just looked up at the roof of your own house and wondered how it defies gravity? How does something so massive stay perfectly sturdy through, say, a raging storm or even a tremor?
It's something we definitely take for granted. You see the finished building,
Right.
but you don't see the intricate silent dance of forces happening inside.
Right. It feels almost magical sometimes.
It does, but it's certainly not magic. It's all governed by a really fundamental concept in engineering,
Mhm.
one that dictates how every single pound of weight, every gust of wind, every shake is meticulously handled.
And that critical concept, you, our listener, is called the load path. Today, we're going to take a deep dive into exactly what that means.
Yeah, what is a load path?
Yeah.
Why is understanding its sort of logical steps absolutely crucial for safety, for the long-term endurance of any structure?
Exactly. And we'll look at how these invisible pathways are considered in design. And for this deep dive, our insights are mainly coming from a great article called Load Transfer in Residential Structures from Roof to Foundation.
Right. So let's start peeling back those layers. When we talk about a load path, what we're basically describing is the precise journey,
Uh-huh.
the route that all the weight on a structure takes.
Okay.
Think about it. The weight of the roof itself, the walls, the floors, furniture, people walking around, maybe even snow piled up.
Mm-hmm.
All these loads, they have to go somewhere
They
specific.
can't just disappear.
No, exactly.
Yeah.
So this journey starts right where the load is applied, and then it travels, pretty methodically, through a whole series of connected structural members, beams, columns, walls,
Mm-hmm.
all the way down through the foundation. And eventually, hopefully safely, it disperses into the ground underneath.
So it sounds like a carefully planned relay race. The weight is the baton.
That's a great analogy, actually.
Yeah, and every beam, column, wall, the foundation. They're all runners, passing that weight along faithfully.
Precisely. And the real genius of a well-designed load path isn't just brute strength, you know? It's about predictability. It's about calculation.
Calculation, how so?
Well, the goal of an efficient design is to distribute all those loads throughout the structure in a very specific, calculated way. It's designed so that no single component gets overloaded.
Ah, okay. That makes sense. Overloading sounds bad.
It is. It can be catastrophic. So engineers can figure out exactly how forces will travel, which lets them optimize every single beam and column. They don't over-engineer things wastefully, but they absolutely guarantee safety.
So it's like this delicate ballet of forces you mentioned.
It really is, making sure every piece carries its specific share of the burden, but no more. Nothing gets overwhelmed.
That really hammers home the importance, doesn't it? This isn't just some abstract idea for engineers.
Oh, absolutely not. It's
Yeah.
fundamental to a building's structural integrity. Its very existence, really.
So a deliberately designed load path that ensures weight gets transferred safely and efficiently.
Exactly. And if you don't design for it properly, if there's like a weak link somewhere, or maybe a connection is missing in that chain of responsibility,
Yeah.
then you end up with a structure that just isn't sound. And that can lead to serious safety hazards. Anything from cracks appearing in a wall, which is bad enough,
Right.
to, in really extreme cases, partial or even total collapse. And even if it doesn't collapse, you're looking at potentially incredibly costly repairs later on.
Wow. Okay.
That's why understanding load paths is just non-negotiable
Mhm.
for structural engineers, architects, building designers, anyone involved in putting up buildings. It's all about building for resilience for the long haul.
Okay, so we've got a handle on what a load path is and why it's so vital, but you mentioned different kinds of loads earlier.
I did, and this is where it gets really interesting, I think.
It's not all loads are the same.
Not at all. Different types require distinct, sometimes surprisingly different load paths. The two main categories we talk about are gravity loads and lateral loads.
Gravity and lateral, okay.
And it's fascinating how engineers tackle these different forces, these sort of ingenious solutions they've come up with over time. Let's start with gravity loads. They're probably the most intuitive ones for most people.
Right, things pulling straight down.
Exactly. Gravity load transfer is simply that process where the weight of a building, its own inherent weight, plus anything inside it gets transferred downward through its structure to the ground.
Could you maybe walk us through an example? Like, how does that work in a typical two-story house? Something we can all picture.
Sure, absolutely. Let's imagine the roof on a standard two-story house. You've got shingles, maybe some snow. That weight pushes down first onto the walls directly beneath the roof edges.
Okay.
Those walls, in turn, they transfer their own weight plus that roof weight
Yeah.
down to the floor structure below them, the second floor in this case.
Got it.
And that second floor, which is holding its own weight,
Mm-hmm.
plus furniture, people, whatever,
Mm-hmm.
it's supported by a network of beams and joists.
Mm-hmm.
So all of that weight from the very top, through the walls, through that second floor, it all needs to make its way, step by logical step, down to the first floor, then through the first floor walls or columns.
Down to the foundation.
Precisely. Down to the foundation. This happens via the load-bearing walls, maybe some columns, beams.
Mm-hmm.
They're all working together like a system of vertical channels.
And the goal is even distribution, you said.
Meticulously even distribution, yeah. You don't want one corner of your foundation sinking because it's taking way too much load.
Right.
And then finally, that foundation acts as the last runner in our relay. It transfers that huge accumulated load safely into the stable ground underneath for support.
Okay, that makes sense. And within gravity loads, you mentioned two types, dead loads and live loads.
That's right.
Sounds simple, but I bet that distinction creates some design challenges.
It definitely does. Dead loads are the permanent ones. They're always there. The static, unchanging bits.
Like the weight of the walls themselves.
Exactly. The structure itself, the roofing materials, maybe fixed equipment like a big water heater or built-in cabinets, they follow that main, constant roof-to-foundation path we just described. Pretty straightforward.
Okay. But then live loads.
Live loads. Those are the tricky ones. They're dynamic, they're temporary, they change over time.
People, furniture.
People walking around, yeah.
Oh,
Furniture being moved, even the weight of snow on the roof, which obviously varies, or heavy rain pooling. Those are live loads.
right. So live loads must need a slightly different approach then, because they aren't always there, or they might be concentrated in one spot for a while, like a big party.
That's exactly it. They can be cyclical or applied unevenly. Think about a sudden rush of people in one room, or maybe a really strong gust of wind pushing against a snow-covered roof, or even just rearranging heavy furniture.
So the load path needs to handle fluctuations.
Precisely. It needs to be designed not just for a predictable static weight, but for these fluctuating, sometimes unpredictable forces. The building needs to be able to kind of flex and absorb them without getting distressed.
So how does that work differently?
Well, while the dead loads follow that main downward path, live loads often need a more, let's say, nuanced approach because they aren't uniformly spread out.
Okay.
So, for instance, the weight of people and furniture on a floor is usually distributed across the floor. Joists first, those are the horizontal beams under your floorboards.
Right, I know those.
Those joists then transfer that load sideways to the supporting walls or maybe to main beams, and then those walls or beams send the load down towards the foundation.
Ah, so there's an extra step, almost. Spreading it out first.
Kind of, yeah. This specific, more flexible design for live loads is crucial. It stops any one joist or beam from being suddenly overloaded if you have, say, a big gathering or after a really heavy snowfall. It's all about designing for the unexpected peaks.
Okay, that covers the vertical journey, the downward push. But what about forces acting sideways on a building? That brings us to lateral load transfer. Sounds like a whole different beast.
It truly is a different ballgame. Horizontal forces think powerful wind gusts slamming against a tall building, or the sudden, violent shaking from an earthquake.
Yeah.
These are temporary loads, but they act laterally, side to side, on the building, and they absolutely demand a distinct and, frankly, incredibly robust type of load path compared to that direct downward journey of gravity.
It can't just go straight down anymore.
No way. The key insight here isn't just that buildings resist sideways forces,
Yep.
but how they do it. It has to be holistic. It's a complex system working together, not just one strong wall trying to do all the work.
Sure.
The goal is to distribute that sideways force across the entire structure, turning what could be a catastrophic push on one point into a manageable, distributed stress that the whole building can handle.
So how do buildings actually do that? What are these specialized systems?
Well, buildings use specialized resistance mechanisms. Two of the main ones are called shear walls and moment frames. Shear walls. Think of them as really rigid walls, often made of reinforced concrete or masonry, built strategically inside the structure. They're specifically designed to basically collect those lateral forces and transfer them down to the foundation. They do this using the building's floors and roof, which act like stiff plates or diaphragms, to channel the force into the shear walls. They're like giant internal braces, stopping the building from racking or leaning over sideways.
Okay, like internal buttresses almost. And moment frames, how are they different?
Moment frames work a bit differently. They form a rigid skeleton, usually using columns and beams, but the key is the connections between them. These connections are engineered to be super strong, fixed joints.
Fixed connection.
Yeah, really rigid. They
Yeah.
can withstand significant bending forces, engineers call these moments that arise from those lateral loads trying to bend the frame.
Yeah.
These bending forces are then transferred directly through the columns down to the footings, deep in the ground. So with both shear walls and moment frames, the ultimate goal is the same. Make sure the building can take those lateral hits without structural damage.
So it maintains its stability even if it sways a bit.
Exactly. It needs to be resilient enough to maybe sway slightly,
Yeah.
absorb that energy, and then return to its original position safely.
That really reinforces that idea of a continuous chain, even for sideways forces. It's fascinating stuff. So let's see how these principles actually play out in different kinds of structures we see every day.
Yeah, let's look at some real-world examples. It's where these concepts really come to life. We can start with something familiar, like a typical timber residential structure, a house.
Okay, our standard house again.
Right. These generally focus much more heavily on the gravity load paths. Why? Because usually they're less susceptible to the most extreme wind or seismic loads compared to, say, a really tall building. So the dead loads often drive the design.
So for that timber house, remind us again, how does that weight get down step by step?
Okay, let's trace it. Roof load shingles, wood. Everything pushes down. First point of contact is often the ridge beam, that main beam at the very peak of the roof.
The spine, right?
The spine, exactly. From there, the load travels down the sloping roof rafters, those angled beams going from the ridge to the walls.
Like ribs.
Like ribs, good one. These rafters then land on the wall plates, which are the horizontal timbers sitting right on top of your walls.
Exactly.
Then the weight travels straight down through the vertical studs, the wooden members that frame your walls.
Okay.
And the studs carry that load down finally to the sole plate, which is the bottom horizontal timber of the wall. And that's usually bolted directly onto the foundation.
So each piece supports the one above it.
Perfectly put. Each member supports the components above it, systematically transferring the load step by logical step, right down to the foundation and then into the ground. Very clear path.
Crystal clear. Okay, now let's scale up. What about something much bigger, like a concrete commercial high-rise? The loads there must be immense.
Oh, absolutely immense. And the stakes are much higher, too. High-rise concrete buildings are designed for really critical load combinations. They have to handle not just gravity, but also potentially huge lateral loads.
Because wind and earthquakes hit them harder.
Much harder. Wind forces increase dramatically with height, and earthquake forces can create enormous bending stresses at the base of a tall structure. So the design is significantly more complex. It's almost like engineering a giant flexible tree that needs to bend without snapping.
Wow. So how do those different loads travel in a concrete giant like that?
Okay, for gravity, the vertical loads, the path is actually quite elegantly direct in those cases. It goes from the roof down through the huge concrete floor slabs on each level. Those slabs act like rigid plates. They transfer the load directly to the massive columns, which run like pillars all the way down to the building's height.
Right down to the bottom.
Right down. From the columns, that massive accumulated weight goes into deep foundations, maybe piles or caissons, that might go down hundreds of feet to reach solid bedrock.
Okay, that's gravity. But the lateral, the horizontal loads.
Ah, that's where the specialized systems really kick in. Those powerful wind or seismic forces hitting the side of the building. They're first transferred from the exterior walls or cladding into the floor slabs, which act as those stiff diaphragms we mentioned.
Okay.
The diaphragms then channel these forces into the building's core, often a central cluster of strong walls, or into strategically placed shear walls or moment frames spread throughout the floor plan.
And those funnel it down.
Exactly. They funnel those forces down to the foundation. And the foundation for a high-rise isn't just sitting there. It might be specifically designed to grip the earth, essentially pushing back against those lateral loads by transferring them deep into the surrounding soil.
You can really see the complexity ramping up there compared to the timber house. It needs that whole integrated system for the sideways forces.
Definitely. Much more involved.
Okay, one more example. Steel portal frames. You see these a lot in like warehouses or big industrial buildings, right?
That's right. Steel portal frames are super common for those kinds of structures. Warehouses, factories, aircraft hangars, they're often a more straightforward load-bearing system, really efficient for creating large open spans.
So how does their load path work? Is it simpler?
It's generally quite direct, yeah. The Roof load, metal sheeting, insulation, whatever, first lands on purlins. These are horizontal beams running across the roof structure.
Okay.
The purlins collect the load and transfer it to the main sloping rafters, which form the angled part of the frame. These rafters then connect directly to the tall vertical columns.
How do they connect? That seems important.
It is. Usually it's done with a welded end plate. Basically, a thick, flat piece of steel is welded to the end of the rafter, and then that plate is bolted very securely to the column. This creates a really strong, rigid connection.
Ah, that makes the portal shape.
Exactly, that strong connection is key. And then the load travels straight down the column to the concrete foundations in the ground.
And can these portal frames handle both types of loads, gravity and lateral?
Yep, they're designed for both.
Yeah.
The columns themselves, combined with those rigid connections, can resist bending forces. Or sometimes they add diagonal bracing members between the columns to make the whole frame even stiffer against sideways sway. So they effectively resist both the downward gravity loads and those lateral wind or seismic forces. Very robust for their intended use.
What really stands out to me listening to all this is how across these completely different structures, a cozy timber home, a massive concrete tower, a sprawling steel warehouse, that fundamental idea, the load path, is always there. It's always about that methodical transfer of weight and force from where it starts all the way down to the ground, using that continuous chain of strong parts. It's like this invisible network of strength holding everything up.
That really is the core message, isn't it? Understanding the load path is just such a critical piece of designing buildings. It's literally what ensures a structure's weight gets transferred safely, efficiently, stopping any one part from getting overloaded and failing.
Right.
And by designing these proper load path mechanisms, whether it's for gravity or for those powerful lateral forces, engineers create buildings that can stand up to everything thrown at them. It ensures safety, ensures longevity for decades, sometimes centuries.
Building a legacy of stability, as you said.
Exactly.
So what does this all mean for you, our listener, as you walk around the built world?
Well, this whole deep dive understanding load paths, it's what allows for optimizing all these structures, residential, commercial, making them safer, more efficient, longer lasting.
And it's not just about painstaking manual calculations anymore either.
Oh.
No, the source material mentioned this too. There are sophisticated software tools now that can dynamically track all these loads and the reactions throughout a structure. They update automatically if the design changes.
Wow, that must speed things up dramatically. It streamlines the whole design process, makes it faster, potentially more cost-effective, and helps engineers create even more structurally efficient and resilient buildings in the end.
That's incredible progress.
It really is. And maybe it raises a final thought for you, something to ponder now that you have this insight.
Yeah.
Now that you know about these sort of invisible highways of force running through structures, how might you look at buildings differently from now on? What kind of load paths do you think are at play in the buildings you see every single day? From a big bridge over a river to the multi-story parking garage downtown, maybe even just your local grocery store.
Right. Thinking about what's holding it all up.
Exactly. How might understanding these invisible forces, this quiet engineering, change the way you appreciate everything that's standing around us?